The job today, I have a phylogeny and I want to calculate distinctiveness of all the terminals. Now, I'm pretty sure I've done this already for an earlier project. So firstly I'll need to try and find that and then go through the commands again. This may be very easy to do, in which case this will be a pretty short video, or it could be awkward and there will be some processing required. Let's try this anyway. But here's a phylogeny and I want to calculate distinctiveness of each of these. So first thing I'm going to do is I'm going to go through some of my old notes and try and find commands to do this. Okay, I think I've found this. So this is an old project and which went through a very large exploratory phase, and distinctiveness is one item which I don't think even made it into the final manuscript, but it seems that Picante R package has a function for distinctiveness. So we will read copy some of these commands over for reading the phylogeny into R, load the package, and it seems that this function here seems what we want to be doing. So copy these over. So I've copied the tree, so species level phylogeny, into the working directory and call it this simple name here. And we use the read tree command in R to read in the phylogeny. So launch R, read in the library, which has quite a lot of phylogeny functions, including the function to read in, including the functions of ape. So we've read in our tree successfully with which is good. No error message returned. 1,612 terminals of the phylogeny. So let's go ahead and try this. This seems to be the function we are looking for here. So we've read the tree into an object. We just call it T1 simply, and we will. So this is our function performed on the tree variable, and the result goes into this item here, which we'll just call this. Okay, let's see what happens. And let's look at the object. Okay, the build is simple enough. We have the value for each of our terminals. Seemingly giving distinctiveness. Okay, so It looks like there's different ways to calculate distinctiveness. So it seems to have equal splits and fair proportion. So we'll probably use both of these. Now we can look at the details of any our function. We just need to give the function name and a question mark just in front of it, and that will load the help page. Yeah, so we have the correct thing here, and two indices of this concept here. Okay, seems simple enough. So we'll calculate based on these two. So yeah, we'll call this ES for equal splits and FP for fair proportion. Okay, finished. So a couple of things. It's always better to check you have sensible results. Now, firstly, what I would do is I'd do a correlation between these two results. I wouldn't be surprised if these were very highly correlated, but we should probably confirm this. Okay, so the results file, the results object is a table with 2 columns, and the row numbers are exactly that, the sort of an index of the object, is not a particular column of that. So I think if I'm going to do a correlation between these two variables, I would do this. I think the safe way to do this would be to use the species to refer to each species. So I think I will first put the row identifiers, which are currently numbers, I'm going to transfer the species names to be instead, and then we can refer, when I do a correlation, we can just refer to the species. So this is a bit more of a safe way to do this. So the species names are in the second column. So in an R table or ROA, we refer to a subset of the object with is 2 dimensions, and so row first and then column second. So in a second, so we'll have nothing here, so that will be all rows and just one item here. So we're just referring to a single column, which is column 2. So this should give us a list of species for this. No, I've done the wrong one. Oh, of course. Okay, so yeah, column 1 is all the species, and these are 1612 and 1612 levels. So that means only one row per unique string. So we'll transfer the species to the row names. So row names of the object is given by this command. Currently there will be should be those those numbers. So we'll put the species as our names. Okay, so transfer the species to the row names. We'll do the same for the other objects, the fair proportion index. Because really I'm not even sure that they're ordered the same, so that's what we're accounting for here. So we will order by the species name, so we're plotting the same. When we do a correlation, we're plotting according to each species. So we'll just do a plot. I'm going to have X and Y. I'm going to plot the index of each, which is in the second column. But for so we're not going to plot these in order. Just to do it safely, we're going to refer to the species list, and we can use just one of these. So we're using a consistent set of species, and that will order them the same regardless of how they are ordered in the tables. So I think this. Okay, so we just plot X and Y. I'll give some labels. So X we have equal splits, and the Y label will be the fair proportion. And cover the main title as okay, so these are very, very highly correlated, these two indices, so don't think it really matters which one we use for evolutionary distinctiveness of our terminals and our phylogeny. So we can, after we calculated these variables, we might want to just store them as a table in case we use them for some other purpose. That we would use this to just write it to a table if we're using these variables outside of R, but I don't think I will do that. The only other thing I would do is just to check this is all legit. It would be to plot the phylogeny and then have a look at, check that these are sensible. So let's just do that. So fig tree is usually good for up to several thousand terminals. You can view it reasonably well. If it's over something like 10,000, gets to 10,000, 20,000, then fig tree doesn't really cut it. You'd probably need to use Archaeopteryx, I would use for. Okay, well, nothing hugely different, but I'll just check this. Perhaps this one, Meridon Erymanthius, which is, and then Meridon Dobogenesis, which is about 2.5 times the distinctiveness. So let's just find these on the phylogeny and see, check these look sensible. So Control F to search taxon labels and find. And it should highlight, but it's not particularly clear. Let's think. We'll need to expand. And I think I see it down at the bottom. Okay. Increase the tip label size. And maybe zoom, which will also increase the x-axis. Okay, so I have this Meridon Dobogenesis, which is 2.5 times the distinctiveness of Meridon Erymanthius. Let's zoom. And then expand. Okay. Yes, so it does indeed look several times more distinctive. That looks reasonable from a visual judgment of the tree itself. So always good to manually confirm, because there can be various sources of error. So this looks like a reasonable result. Okay, so I think that's enough. We've achieved our result, our aim today, to calculate distinctiveness, and this requires a rather small number of commands. It can be done in R under the Picante library. So and then once this library is loaded, it's actually just 2 or 3 commands to calculate these values.